Should be okay. So thank you for the introduction, and thank you for the opportunity to present here. The work that I'll be talking about is actually going to involve several topics, and it's actually a cumulative work of several years now and several generations of students, and also some recent collaboration with some industrial partners. So the various topics that I'll be talking about actually extends a little bit beyond just retinal implants or artificial retina, and also a little bit beyond just neuronal stimulations. But neurostimulation is the main theme. But I would also talk about more generally about the use of carbon nanotubes for neuronal applications, and the use of carbon nanotube in microfabrication, so not necessarily just for neurological applications. And ultimately, I'll describe to you also some recent work that we do on using carbon nanotube for optical stimulation of the retina. So when it comes to electrical stimulation of neurons, you could talk about generally the good, the bad, and the ugly. So the good is basically ultimately what you want to achieve, which is high-resolution stimulation and using flexible devices that would not interfere with the biological tissue. So this is some example of something I'll be talking about. This is a soft, flexible electrode, and this is an example of very high, very specific stimulation of a particular nerve cell. But this is not always the case. In many cases, actually, when you do electrical stimulation of neuronal tissue, you end up with something which is very dispersed, very non-local. And I'll show you just a very brief example. And you may also activate glia cells, so there's quite a lot of complexity. It's not as straightforward just as applying voltage or applying a short current pulse and expecting things to behave the way you want them. And it can turn actually pretty ugly in case of when you actually end up with electroporation or even tissue damage, and definitely electrode damage. So it's not so straightforward, but nonetheless, this is a very, very helpful and very important technology. So some just to show some flavor of what does it mean. So electrically, what you're looking at is an electrode. This is a 30 micrometer electrode, and these are cells. These are cells, neuronal cells and glia cells with calcium indicator that gives you an indication for calcium level in the cells, which basically indicate electrical activity. And independently, you see here the trace of the electrical recording. So simple electrical recording can provide very straightforward information about the electrical activity of the cells. In this particular case, where it's an extracellular electrode, it's an accumulative information from several cells that reside at the proximity of the cell. So this is a very helpful technique that we develop in order to better understand what's going on in this process. And electrically, what it means is that you have the electrochemical interface right here. This is the electrode, and you have the cell soma. So this is roughly how we describe the interaction between the electrode and the cell, and what does it mean actually to achieve electrical recording. Now, electrical stimulation is in principle very similar. It's the same circuit, but it's a lot more complex in many ways. So now what you see here, these are 10 micrometer electrodes, and we pass short current pulses through these electrodes, and we just go and stimulate each one separately, as you can see. So every time you see one of the electrodes being highlighted, this is when we stimulate it. And when you look around, you can see that a lot of the cells may actually be activated. So the activation mechanism is actually pretty complex, and it has a lot to do with the way that protein are distributed on the cell membrane, and it's very, very sensitive to exactly how you run the stimulation. So this is just to give a very, very general introduction. And now, where is it being used? So you've heard the presentation this morning. These are just 3 examples. This is a DBS application, deep brain stimulation, where electrodes are inserted into the brain and used to stimulate a very, very specific very localized region of the brain. It's already being used relatively extensively, considering the fact that this is a very invasive, very complex technology. Cochlear implants are also very, very well known, with over 200,000 people with such implants. And probably the last frontier, or one of the main frontiers in this technology, are the artificial retina, or the retinal implants. In this particular case, this is an actual implant developed by a German company, and it's made of an array of photodiodes deposited or basically inserted at the back of the retina. Now, if here we have 1 electrode, here we have something like 16 or 20 electrodes. Here the vision, or the aim, is to achieve something like 600 or even 1,000 electrodes. So there's a huge difference in terms of the requirements going from this technology to this technology, even though principally these are very similar ideas. In all cases, you actually want to stimulate neurons, neuronal cells at very, very high resolution. So just because I'll focus on retinal implants, I'll just say very quickly, this is the retina. The retina is located here at the back of the eye. It covers almost the entire range of the back of our eye, and it's made of several cell layers. The most outer one, the one at the back, is actually the photosensitive one, and this is a layer that tends to deteriorate in several situations, including a very famous one, which is the AMD, the age-related macular degeneration. There are also some genetic degenerative diseases, but generally what happens is this layer basically becomes dysfunctional and is practically gone. And therefore, in order to restore vision, one of these ideas that were presented actually quite a long time ago was to stimulate the neurons, the nerve cells that are located still at the retina and are still quite functional, to stimulate them either by placing a device right here or stimulated by a device that is located right here. And in both cases, you would need to transfer information to the implant or to the electrodes that are deposited here or here. And you end up with, these are 2 examples of devices. This is an epiretina device, so it's located here. This is a subretina device. It would be located here. And in both cases, these are heavily dependent on microtechnology. In two respects, so the microtechnology basically has 2 fundamental things that we have to consider. The fact that it's made of many elements of microtechnology, but ultimately it's not so micro. It's actually pretty large. So overall, this is a centimeter. Each one of these is several centimeters in size. The other issue that it relies heavily on materials and processes that were developed in the micro technology, even though they went through adaptation for these applications. So this is kind of the background. Now, in terms of the existing technologies, so most of the electrodes, or the electrodes that are being used most commonly, are noble metal electrodes. There are several variations, several different materials that were proposed, but this is generally the metals, the electrodes that are being used. Of course, there's the issue of body rejection, plus the issue of rigidity, which is a very major concern when it comes to interaction with biological tissue. And generally, the other very critical issue is the attachment between the device and the physiological tissue. Ideally, if you now move to the domain of what you would like to have, electrodes which are very flexible. Ideally, these should be, since we're talking about electrochemical electrodes, ideally these should not be Faradaic electrodes, but actually capacitive electrodes. Ideally, you want to have systems without corrosion, with simple fabrication, and hopefully something that can actually interface very simply with the physiological system. So what we've been doing over the past several years, as I said before, it's actually an ongoing activity, was to first identify carbon nanotubes as a very attractive system for these applications. So it really started from identifying two very important parameters that make carbon nanotubes very attractive for this application. So if anybody here doesn't know what carbon nanotubes are, it's actually, these are multi-wall carbon nanotubes. So these are concentric cylinders made of basically carbon tubes. And I mean, who doesn't know what carbon nanotubes are? So, so the first very, very important feature is the fact that it's very easy using various methods to grow very high density of carbon nanotubes. And the advantage of this approach is the fact that when you look at the biological interaction, the carbon nanotube acts as a very nice Velcro-like material. So these are examples of neurons, and it's very, very easy to show that neurons and neuronal tissue, more generally neuronal tissue, can adhere very, very effectively to this interface. Now, because of the chemical structure of carbon nanotube, this is also a very stable material. It does not, it's very inert, and therefore, in that respect, very biocompatible and very stable in the electrophysiological condition. The other thing is that, again, since we're talking about electrochemical or electrochemistry here, the electrode, either for recording or for stimulation, has to be ideally capacitive electrodes, so especially for stimulation. So this is really the case for a carbon, essentially carbon electrode. It also is very stable. So mechanically, if you think about a very porous material would not necessarily be very stable. So if you think about platinum black, for instance, it's not a very robust material. In this particular case, it's very robust. So we can actually grow these films, and we can actually perform very high signal-to-noise ratio recordings with these electrodes. But really what we did over the past several years was to take all these ideas and actually implement them using carbon nanotubes on flexible substrates, and try to take all these benefits into a system that can actually be used in vivo. Now, the other, basically the third major benefit of carbon nanotubes in this particular case is that when it comes to making bendable electronics, it's a very, very good system, right? Because this is not just a thin film. This is actually a spaghetti-like film, and therefore is very compliant with bending. So it's very nice fit with this application. And again, at the very end, I would also say something about the ability to turn these things into photosensitive elements, so we can actually run optical stimulation with them. So this is an old work where we use pretty standard microfabrication, and you can actually grow carbon nanotube as integral part of your multi-electrode array, and you can use these electrodes to convince yourself about the electrochemical and electrical properties of these systems. This is something that I mentioned before, so you can actually culture cells on these surfaces, and you can actually show that there's a very attractive interaction between the biological tissue and the system. These are the electrochemical properties, so just keep in mind that it's a very, very rough and very robust substrate. And therefore, when you actually measure the electrochemical, the cyclic voltammetry, and try to figure out what's the electrochemical impedance, or basically the specific capacitance, you can actually show that it's a very high effective surface area and relatively purely capacitive electrodes. So these are the important features. When it comes to electrical recording, as I said, you can actually get very high signal-to-noise ratios, just because there's nothing, it's not something magical about the carbon nanotubes, it's just because it allows this very, very nice binding between the tissue and the electrodes. This is something you can actually see here. This is a cross-section of a retina that was cultured on carbon nanotubes for 48 hours, and you can see how nicely the tissue integrates into the carbon nanotube. So the two things become very intimately connected. And when you compare conventional titanium nitride electrodes with carbon nanotube electrodes, you see that titanium nitride electrodes basically have a certain base level of signal to noise. With carbon nanotube electrode, we just see that the signal to noise ratio just gets better and better. Basically, what we think is that it corresponds with this feature where the tissue, so if this is the tissue, it just gets more and more intimately contacted by the carbon nanotubes. So how do you turn all that into a flexible substrate? So carbon nanotube, at least the carbon nanotube growth we use here is very high temperature process, so you really have to work out a special procedure how to do that. And what we did was to transform the substrate that we use for the growth. So if conventionally we use titanium nitride and use basically nanoparticles as the seed layer for the growth, for the flexible electronic application, we just skip the titanium nitride. So what happens is that the carbon nanotube growth is pretty loose on the substrate. So it's pretty much the same thing. The only difference is if here the carbon nanotubes are basically anchored, contacted very, very tightly to the substrate. In this particular case, they're bound pretty loosely. And so what you can do next is something pretty simple. You can grow the carbon nanotubes, and then if you just take some polymer material and you apply it on the carbon nanotube, you can then peel the whole thing off. So you can take the entire circuit, and then, of course, you can make your passivation layer with an independent molding procedure. You combine the two things together, and you end up with a working device. The nice thing is that you can use many, many different materials in order to do this transfer. So you can use, of course, the PDMS, but you can use various medical tapes and sellotapes and polyamide and Parylene C and gelatin that we tried, and lots of other things. It's, of course, important to validate the electrical conductivity, so not just the electrochemistry. So these are two independent things that you have to work out for this application. In order to validate the electrical conductivity, we made these test structures, and then we can systematically do the electrical measurements and validate the electrical resistivity. And in this particular application, these are, it doesn't look like extremely fantastic values, but for this application, this is more than enough, considering the fact that you're limited by the interface impedance rather than by this resistivity. And of course, the electrochemistry is a very important feature. It's probably the most important feature. And again, we get very similar results to what I've shown you on the silicon substrate. So this is, again, cyclic voltammetry. So this is current as a function of voltage in a 3-cell setup in PBS using different electrodes of different sizes. And you can, again, systematically measure the capacitance, and from that derive the specific capacitance, and you can really confirm that you have a very high density, high surface area capacitive electrode. The important thing, though, is that even though I showed it as if it's quite trivial, it's not at all trivial. The major challenge here was how to avoid clogging the entire film by the polymer. So since the polymers have to be insulating, there's a very tricky trade-off how to do it. So there's actually great amount of details in how you actually deposit the polymer and how you remove it, and it's not at all trivial. But the bottom line is that if you know how to do it, you actually end up with a pretty nice, very simple protocol of how to produce flexible electrode with really high very good electrochemical properties using a very simple, pretty straightforward process. So no need for multiple preparations and multiple processes. And to validate the properties of these electrodes, of course, I've shown the electrochemistry, but the ultimate test is using physiological tissue, and we used a retina. This is a cheek retina. You can dissociate it and put the cheek retina on these electrodes, which are bound on a PCB support, and you can use a very simple test. You run stimulation on one of these electrodes, and you can use nearby electrodes to see whether you have electrical response. And this is the kind of testing you do to actually validate that these things actually work, both for recording the electrical activity. Again, you see with fairly high nice signal-to-noise ratio, but also being able to do stimulation at low thresholds. So these are the two important parameters, and to find the exact threshold, you can run different tests at different amplitudes and durations. So the very last 3 minutes, I think, that I have, I'll show you what we're working on right now. And this is actually to take the carbon nanotube, this carbon nanotube setup that I was talking about, to the next level. And the next level is to get rid of wiring, because everything we've done so far is improving the electrodes, but you still need all the wiring to the external input and to the external power. And this is, again, in the application of the artificial retina, this is one of the most challenging issues. Ideally, you want to have something like this. So this is a structure with carbon nanotube island, and this whole thing is basically 3 millimeter in size. It's made of PDMS. And the unique thing that we've done over the past year was to incorporate quantum dots, actually in this particular case, quantum rods, onto the carbon nanotube. So now we have a hybrid system of quantum rods and carbon nanotubes. So when you shine light on this system, you actually can generate charge transfer from the quantum rods to the carbon nanotubes, and you generate a local polarization of the surface. And if it's sufficient enough, if you have enough quantum rods, if the electric field is strong enough, you can actually locally induce electrical activity without the need of external wiring. So this is a related paper that we just got accepted with a related system. This is not the carbon nanotube system, but there are quite a lot of action in this field. The advantage of the carbon nanotubes compared with, say, polymeric solution is the fact that you benefit from all the properties that I've shown before, including the fact that you have a very bioadhesive material. So these are these materials. It took a lot of work to figure out how to do it, because if you think about it, there are quite a lot of parameters. You have to figure out which are the right quantum rods or quantum dots, how exactly to do the conjugation. So there's a lot of chemistry involved. But ultimately, we were able to go and increase the efficiency of this system by several, actually more than 5 orders of magnitude over the past year, down to the point that today we have films. These films were actually deposited on titanium nitride because these are available commercially. And these devices can yield very nice polarization with pretty sizable voltages and also photocurrent. So this is just measuring the photovoltage or the photocurrent building up on these electrodes. And again, putting a retina on, shining light, and we can actually demonstrate electrical stimulation with these films. So the nice thing here is that this is basically direct optical stimulation of a blind retina, okay, a retina that does not have photosensitivity, without any wiring. So it's optically or electrically mediated optical activation. And I think with pretty excellent timing, this is my summary. So the carbon nanotube electrodes are it's not just the fact that it's simple to make. It's really the fact that it's all inclusive. I mean, the whole device is made entirely of the carbon nanotubes. That means that it's also a very clean process, so there are no chemical residues or no other material that can cause degradation of the system. These are capacitive electrodes, flexible, and with low impedance. And these are, of course, the people, or some of the people that did the work. And since, for those of you who come from Europe and North America and start thinking about the coming of the winter, so this is Tel Aviv, probably in a winter day looks just like that. So consider that as an option. Thank you very much. Mm-hmm.
So what are you here? I mean, would you see this possible in the future to where you are still very far from a light intensity that would be easily detected directly and transferred?
Well, I think targeting this one photon sensitivity from where the technology is right now is, it's the greatest challenge is actually, I think, or the big question is whether you should dream about vision in the sense that we think about vision, a functional vision where I can identify different elements, or that we can think of vision more like in the sense of a prosthesis, right? When you make a prosthesis for a hand or a leg, you don't really reconstruct, you don't necessarily reconstruct the original features, but you actually allow the patient with the desired functionality. And I think this is what this technology should do. I don't think, at least in the foreseeable future, I don't think people should really talk in terms of pixels or resolution or these things, because there are so many other challenges that I haven't even described. I just mentioned briefly at the beginning that there's the issue of stimulating axons rather than stimulating soma. So the ability to actually perform local stimulation, and it doesn't matter if it's from the back or from the front, is very, very far away. Well, so it really depends where you're aiming it. So if you're aiming at the optical stimulation, then it's actually pretty easy to make very small features. We can go down to 1 micron, 2 microns. That seems to be, at least as far as the transfer mechanism, it's quite easy. When you want to transfer an entire circuit, including very long conducting tracks, this is a little bit more challenging, but it really depends how you're going to do the process. So at the moment, we do it quite manually. So of course, it's you can't really comment about the limits. It's really, I mean, at the moment, the nice thing is that we started working on this project with some industrial partners, and then it would be actually meaningful to start looking into these issues. So a priori, you can probably go down to several micrometers, but
we have time for one more last question.
So I haven't seen any redox reactions on your CV. Probably one of you were pushing it for
right.
higher voltages, and you're planning for capacitive stimulation anyways. But I was always thinking that capacitive stimulation is hard enough to generate anything in the retina, and you definitely need some redox reaction to inject some charges to tissue. And
Yeah, so, well, generally the charge that you need in order to run stimulation really depends on not just on the electrode properties itself, but actually how you deposit the electrode against the tissue. So if you have very close proximity, and here we work with ideal conditions, right? This is ex vivo. You press the retina against a device, and therefore you are in a position where you can run things at very favorable conditions. Often in retina, in actual implants, the implant itself is not very well positioned against the tissue. And I think this is one of the major challenges, and hopefully this is one of the things that the carbon nanotubes can actually help in the sense that it turns into a very intimate link with the tissue. So this is one issue which really determines how much charge you need. Then concerning the biocompatibility, of course, if you're running non-capacitive stimulation, if you run Faradaic processes, then it shouldn't be too biocompatible in the long term. Of course, this is what a lot of people do ultimately, but this is far from being an ideal situation.
Just thank you